which is the electrolysis. And these are, actually I lied. This is the next to last part. The last part is definitional corrosion. But this is the last part involving numbers. Now, electrolysis are non-spontaneous cells. Spontaneous as they go. What we have is chemical reactions are caused by the flow of electrons. But in the case of electrolysis, what we're doing is we're using current to pump electrons in and move the reaction in reverse. So the net force behind electrolysis is we're forcing a reaction in reverse. Now, there are a couple things that stay the same. Reduction still occurs at the cathode. But now, instead of the electrons being given or gained spontaneously, you're forcing them to be taken. So sodium wants to give up its electrons. Well, in electrolysis, you force it into the elemental form. Okay, and because you're reversing it, we said that the cathode was positive because the electrons were being attracted to it. Well, now you're forcing them in, so in electrolysis the charges change. So cathodes are negative, anodes are still where oxidation occurs, but now they are positive. And again, you're forcing the reaction in reverse. Now, this is what is done to plate objects. So, for example, if you're trying to put nickel, and that's what they do to chrome out a vehicle, or in this case, they're putting the nickel on, looks like a steel ring. So basically, they're chrome plating it, and what you'll notice is the anode is still written on the left, the cathode on the right, but now the charges are opposite because we're forcing them to go in reverse. Okay, so a real interesting reaction that takes place this way is, and this is what they talk about when they talk about having a hydrogen car. This is one of the aspects of it. You can take the water and generate the hydrogen and the oxygen, which with to burn it. If you have a power source and you have water, and again, we still need our circuit, so this is our FRET or salt bridge. What you're doing is producing oxygen gas over here and hydrogen gas over here. Notice that this is 2-to-1 size-wise. Over here, you got the same thing. This is the hydrogen and this is the oxygen. And so you can use electrolysis to produce hydrogen and oxygen gas from water. Okay. This is a slide I found years ago, but this is how they electroplate Oscars. And this is why if a movie star loses an Oscar due to a fire, somebody steals it, etc., it's really hard to replace because they only make what they need and they label them, etc. Okay, so rules associated with electrolysis and aqueous solution. Now, the trick to aqueous solutions is if you're going to do electrolysis on anything, then you have a problem because water was going to interfere in the reaction as it goes forward. Okay, so you have to take this into account. So metals can be reduced if E-red is greater than negative 0.82 because that's the reduction of water. And then oxidation, and this is the oxidation of oxygen. Okay, so the bottom line is if you go to work in this field, you will have to worry about water. But since we're playing on paper, we're get to ignore these rules, and we're going to pretend that there is no water present. But one other thing I want to say before we do the water present, it gives you different products. So if you take molten sodium chloride, and that's a major conductor, If there's only sodium chloride present, you get sodium metal and chlorine gas. If there's water present, you get caustic soda, which is sodium hydroxide, and chlorine gas. Now, the next time you're stopped behind a train, you might want to watch the rail cars as they go by, because a lot of them you'll see, depending on where they're coming from, will have chlorine gas or caustic soda on them. Because if they're working to electrolyze or hydrolyze water, then there's usually, sodium chloride, then there's water present. That these are commonly sent by rail cars. Down around Savannah, they're on barges. So it's just kind of interesting to watch. I remember for chlorine gas, this is a yellow gas. It's very heavy. So if you see a cloud of it, walk away. Don't run towards it. Okay, so what we're going to do is we're going to pretend that we have no water, because we could do that on paper. And if we do that, then Faraday's law comes into play, which is the amount of a substance consumed or produced at one of the electrodes in an electrolytic cell is directly proportional to the amount of electricity that passes through the cell. Wow. Okay, so charge is current times time. 1 amp is a coulomb per second. And a mole of electrons is that many coulombs. That's Faraday's constant. Okay? And it doesn't matter what we're doing, you must count the number of electrons that pass through. So, when you work a problem, just like anything else, it really boils down to stoichiometry. And you've got to count. So, you start with an amount. In this case, we can start with the current times the time. That'll give us the moles of electrons. We can go from current to moles using Faraday's constant. Then we go from moles of electrons to moles of species using the moles of electrons needed. Okay. Then you can go from the moles of the species to their mass using the atomic mass of the species. Now, we will have charged species like nickel 2 plus to nickel, chromium 3 plus to chromium. The mass is not affected by the gain or loss of electrons because electrons pretty much are minimal. So we're going to use these conversions. And remember, you will be given Faraday's constant, and you will be given that 1 amp is equal to 1 coulomb per second. Now, it's like everything else. You can say it's 1 coulomb per second, or in 1 second you get a coulomb, which is, an inverse amp. So here we go. Electrolysis. What mass of nickel will be deposited at the cathode of an electrolysis cell if a current passes for 1 hour through an aqueous solution containing excess nickel? Okay. So what we're really looking for is the grams of nickel. Before we go into that, we're going from nickel 2 plus. It's going to gain 2 moles of electrons to give us the nickel metal. Okay, now we're going to start with an amount, and our amount we've got is going to be 1 hour. Okay, so you can do this a variety of ways, but 1 hour, we know that 1 hour is equal to 60 minutes, and we know that 1 minute is 60 seconds, or for those of you who can do this are like, oh wait, that's just 3,600 seconds, and that's fine. So you can write it in there. So we've gotten rid of our minutes and our hours, so we're down to seconds. And we know that if our milliamps, that means per every second we've got 0.020 amps, coulombs moving through, because this means that this is 0.02 amps, which means it's 0.02 coulombs per 1 second. So our seconds are gone. We're left with coulombs. And we can use coulombs. We know that there are 96,485 coulombs per 1 mole of electrons. That's Faraday's constant. And we have 2 moles of electrons. for 1 mole of nickel. And we know that 1 mole of nickel has a mass of 58.69 grams. So if we run all the numbers, remember everything on top is multiplied and everything on the bottom is divided, we should get 0.021898 grams. So if we're keeping 4 non-zero digits, we get 0.021990 grams of nickel. Now what that means is if you're using milliamps, that's a very short, very low power. So if you're moving it through an hour, you're still getting that much nickel, which depending upon what you're coating, that may be more than enough. If you're coating something large, that is not enough. So what we're going to do is we're going to look at another problem, and we're going to look at it in reverse. So if you apply 0.5 amps for 90 minutes, how many grams of silver can be plated out? Okay, so remember the 0.50 amps is equal to 0.50 coulombs per 1 second. And we know that silver is 1 plus, so we'll need 1 mole of electrons for every mole of silver. And we've got the 90 minutes. So we're looking for grams of silver again. So we're going to start with our time, which is 90 minutes. And we know that 1 minute is 60 seconds. So our minutes are gone. And we know that we have 0.50 coulombs per 1 second. And there are 485 coulombs per 1 mole of electrons. Again, Faraday's constant. And we get 1 mole of electrons is needed for every 1 mole of silver. And 1 mole of silver is equal to 107.87 grams. So when we run the numbers, we get 3.018 grams of silver plating out. Okay, so you will have one like this on the test. It's relatively simple. It's just a matter of walking through and following your units. Now, the one on the test is probably going to be more along the lines of this one right here. And this one takes a little bit more. In some ways is easier, in other ways is actually the same with just one extra step. It says write out the reactions that occur at the anode and cathode and label them. So remember, if this splits up, this is rhenium 7 plus 7 bromide ions. Okay, so what we have here is rhenium 7 plus 7 electrons will give you the metal. Okay, that is gaining electrons, so it's reduced, so that's the cathode. And 7 bromides are going to reduce to 7 halves bromide 2 plus 7 electrons, and here we're just balancing electrons. This is the anode. If you were to work this and use an even number of bromines, I wouldn't have a problem with that. But remember, this is oxidation, so it goes at the anode, and rhenium is reduction, so it goes at the cathode. Now, question on this one is how many hours? So this one we're going to work in reverse, and we're going to start with the amount, which in this case is the grams. So we're going to start with 35.8 grams of the rhenium. We know that the atomic weight is 1.86.207 grams per 1 mole of rhenium. And we know that 1 mole of rhenium takes 7 moles of electrons, and that 1 mole of electron is equal to 96,485 coulombs. and we know that our amperage is 3.53 coulombs per 1 second. And we know that there are 3,600 seconds in 1 hour. So when we do the math, we get 10.21804 hours, or 10.2180 hours. Okay, this is what it would take to plate out that much of the rhenium. Okay, and again, this is very similar to the previous ones, except the previous ones we started with our amperage and our time. In this case, we started off with our amperage and our mass, so we calculated it backwards. It doesn't matter as long as you use your units, and your units will tell you where to go and what to do next. You are good to go on this. And our last slide has to do with the electrometallurgy of aluminum. Everybody takes aluminum for granted, but aluminum is actually a fabulous metal to have. However, until they figured out a way to mass produce it, and it was two young adults, they were in their late teens when they started. They didn't have a formal degree, and they were working in sheds. So you might want to read through this, because you can achieve anything you want if you put your mind to it. So this is kind of just one of the interesting history things.